The paper we're unpacking today is Latent Collaboration in Multi-Agent Systems, coming from researchers at Princeton, UIUC, and Stanford.
And this one is a big deal. They've built a framework called Latent MAS, and it lets LLM agents collaborate entirely in the latent space. No text.
And the results are just, they speak for themselves. We're seeing huge performance gains.
Oh, absolutely. It's a training-free framework, which is key. And it's consistently outperforming text-based systems. We're talking up to a 14.6% accuracy jump in some cases.
But the number that really blew me away was the efficiency. It's not just a little better, it's a completely different league.
Yeah, you're looking at cutting output token usage by, on average, 70 to 80%.
It means it's faster.
Way faster, around 4.3 times faster end-to-end. And that's against already optimized text systems. It's just a fundamental shift.
Okay, so let's break down the problem they're actually solving. Multi-agent systems like AutoGen or MetaGPT are everywhere now. They're essential for complex tasks. But they all talk to each other using text. Natural language is their, lingua franca.
And that's the bottleneck. That's the entire problem statement of this paper.
Why is text the bottleneck? Isn't that what these models are best at?
It is, but think about where the actual thinking happens. It's in the model's internal hidden states, this massive high-dimensional continuous space.
It's all just vectors and floating point numbers.
Exactly. And when Agent A wants to tell something to Agent B, it has to take that rich, continuous thought and basically crush it down into discrete tokens.
It's like taking a high-resolution image and saving it as a super compressed, lossy JPEG.
That is the perfect analogy. And then Agent B gets that lossy JPEG, the text, and has to try and reconstruct the original high-res thought from it.
Which sounds incredibly inefficient.
It is. It's slow because decoding and re-encoding all those tokens takes a ton of compute, and it's lossy. You lose nuance. This is how errors get compounded down the chain.
So the big question they asked was, can we just skip the text part entirely?
Can we have pure latent collaboration? And their answer, Latent MAS, is built on two really clever components.
Okay, let's unpack the first one. How does an agent even think for itself in this latent space? This idea of auto-regressive latent thoughts.
So the first big change is what the model actually outputs. Instead of generating a token at each step, it's set up to generate its own last layer hidden representation, a vector.
So it's basically talking to itself in its native language of vectors.
Yep. It generates a stream of these vectors, which is its internal chain of thought. But, and this is a huge but, you can't just take that output vector and feed it back into the model as input for the next step.
Why not?
It's a distribution mismatch. The statistics of the output hidden states are totally different from what the input embedding layer expects to see.
So if you do that, the model just gets confused. It sees something completely out of distribution.
It falls apart. You get what they call representation drift, and the whole reasoning process just becomes noise.
So how do they solve that? This seems like a deal breaker.
With something really elegant, actually. A linear alignment operator they call WA.
Okay, what does WAT do?
It's basically a translation key. It's computed just once, using a simple ridge regression on the model's existing output and input weights. It learns how to map an output vector H back into a valid input embedding. So E equals H, WA.
So it's a tiny one-time calibration that makes sure the model's internal conversation stays on track.
Exactly. It's computationally almost free, but it's absolutely critical for stability. The results show it gives a consistent 2 to 5% accuracy boost. Without it, the system doesn't work.
Okay, so that's how Agent A thinks. It generates this stable, continuous stream of thought. Now, how does it pass that thought to Agent B without using text?
This is the second key idea. They repurpose the KV cache.
The key value cache.
Yeah.
We usually think of that as just a speed optimization for attention, right?
Right. It stores past computations so the model doesn't have to redo them. But here, they treat it as a dynamic, shared, latent working memory.
So Agent A isn't sending a message. It's sending its memory.
Its entire memory. After Agent A is done with its latent reasoning, the framework extracts the KV caches from all the transformer layers. This memory contains the initial context plus all the nuance of the new latent thoughts it just generated.
And Agent B just loads that memory state.
It integrates it. It concatenates Agent A's KV cache into its own layer by layer before it starts its own reasoning.
So Agent B is effectively starting its thought process with Agent A's entire context and reasoning trajectory already loaded in. It's like it was there the whole time.
That's a perfect way to put it. It completely skips the re-encoding step. And they prove this with Theorem 3.3. It's a mathematically lossless information transfer. It's equivalent to exchanging the information via text, but just infinitely more efficient.
This brings us to the theoretical side of things. It's faster, sure, but is it actually smarter? Is a latent thought more expressive than a token?
Oh, way more. Theorem 3.1 breaks this down. A continuous latent thought can carry vastly more information than a discrete token.
They have a formula for it, right? It's something like OED shog V.
Yep. So DH is the hidden dimension of the model, which can be thousands, and V is the vocabulary size, maybe 100,000.
So DH is big and log V is comparatively small.
Exactly. The math just shows you the sheer bandwidth advantage of thinking in the high-dimensional latent space versus the restrictive space of discrete words.
And they put a number on it for the Qwen 3 model they used.
For the Qwen 314b model, they calculated that latent thought generation is theoretically over 470 times more efficient at conveying information.
470 times. That's not an incremental improvement.
No, it's a different paradigm, and this is why the complexity scales so much better. Text-based systems are always bottlenecked by that massive vocabulary size. V latent MIS just sidesteps that entire problem.
So if these latent thoughts are so rich, how many do you actually need? I mean, how much thinking is enough?
That's a great question, and they tested it. They looked at a bunch of benchmarks and found this really clear sweet spot.
Where was it?
Performance tends to climb steadily and then peak somewhere between 40 and 80 latent steps.
And what happens after 80 steps? Does it keep getting better?
It actually plateaus or even dips slightly.
Why do you think that is? Does the model just run out of things to say, so to speak?
It seems to be that redundancy kicks in. The core of the thought has been generated, and any further steps are just kind of refining the same idea or adding noise. So it gives you a really practical target. Aim for about 80 steps, and you get all the benefit without the waste.
Let's get into the empirical results then. They ran this on 9 benchmarks, different architectures, different models. Let's talk speed again, because those numbers were just wild.
The speed up is real. They saw between 2.6x and up to 7x faster inference compared to TextMAS.
And that's 7x against TextMAS running on Viv LLM, which is already a highly accelerated backend.
Exactly. It's not a softball comparison. It shows the architectural advantage is fundamental.
And what drives that?
It's just the amount of work being done. On a hard reasoning problem, TextMAS might spit out 20,000 tokens across all agents to write out its full chain of thought.
20,000. Wow.
Latent MAS gets a better answer with fewer than 50 latent steps. The work is dense and internal, not spelled out in slow, expensive tokens.
Okay, but this next part seems almost paradoxical. Latent MAS uses dramatically fewer tokens than TextMAS, obviously. But they say it also uses fewer tokens than a single LLM doing the same task. How is that possible?
I know, it feels wrong at first, right? But it's about the efficiency of distributed work. A single LLM has to generate a very long, explicit chain of thought for you to verify its reasoning. Lots of tokens.
It has to show its work.
Exactly. In latent MAS, the agents show their work to each other in the latent space, which is basically free. The final agent just needs to take that rich, condensed history and output the final short answer.
So all the heavy lifting is invisible from a token cost perspective.
And that's why they saw token reductions of up to 60%, even compared to a single model. It's just a smarter way to distribute the cognitive load.
And this all translates to better accuracy, especially on tough tasks like code generation and math. You mentioned error compounding before, and the GSM-8K case study really highlights this.
Yeah, that case study is so telling. With TextMAS, if the first agent in the chain makes a conceptual mistake in its text plan, the next agent reads that mistake. It might polish the grammar, but it's stuck with the fundamental error.
It's working with a flawed blueprint.
A flawed, discrete blueprint. But with latent MAS, the next agent gets the continuous representation of the flawed reasoning. That high-fidelity context gives it enough information to see the underlying intention and actually correct the upstream mistake.
So it can fix the foundation, not just paint over the cracks.
That's it. And that leads to a correct final answer in cases where TextMAS just fails completely. It's a huge win for robustness.
Okay, so we had the speed, the efficiency, the accuracy. But we have to ask the big question. Are these streams of vectors really communication? Are they meaningful?
They dug into that directly with the semantic analysis. They basically took the embeddings of the latent thoughts from latent MAS and compared them to the embeddings of the actual text tokens from TextMAS that led to correct answers.
So mapping them out to see if they occupy the same meaning space?
Exactly. And the first finding was that, yes, the latent thought embeddings landed in almost the exact same region as the correct text embeddings. So they are semantically consistent. The meaning is there.
Okay, so they're not just random noise. They encode the right concepts.
Right. But here's the even cooler part. The second finding was that the cloud of latent Mayas embeddings was bigger. It covered the space of the text embeddings, but also filled in the gaps between them.
What does that mean?
It points to greater expressive capacity. Think about it like a piano versus a violin. The text tokens are like the 88 discrete keys on a piano. You can play a beautiful melody.
But the latent space is like the violin string.
It's continuous. You can hit all the notes in between the keys. That extra nuance, that higher bandwidth, gives the next agent more to work with, which leads to better, more robust outcomes.
So to wrap up, latent Ming AS feels like a major step forward. It moves multi-agent collaboration from the clunky world of text into the model's native language.
And it does it with huge gains in speed, efficiency, and accuracy, all without any retraining. It's a general framework that can be dropped into pretty much any agent architecture, sequential or hierarchical.
It really feels like a foundational piece for what's next, which leads to a final thought. This whole framework is training-free. It's just clever engineering. But we know that text-based systems benefit massively from post-training, from fine-tuning the agents to communicate better. So what happens when we start applying those same ideas here?
That's the billion-dollar question, isn't it? What if you could fine-tune these latent communication pathways? If you could teach models to optimize these continuous high-bandwidth conversations, what kind of new collaborative behaviors might emerge? We could be looking at a form of intelligence that we can't even describe in natural language because it was never designed to be limited by it.